Hello again and welcome. Today I'm going to continue my topic on waveguides. So in this video I'm going to go over a homemade spectrometer. Now before we get started I want to explain something. We're going to be touching on the subject of quantum mechanics. Don't be surprised if I make a lot of mistakes in this video. There's definitely a reason for that. It's because I don't know anything about the topic that I'm about to discuss. And I want to be clear, I'm not a physicist. So keep that in mind as you're going through this video. I'm probably going to present this material in a unique way, so if you don't know anything about quantum physics or spectrometers, hopefully you'll be able to understand what it is that I'm presenting here. So I mentioned in part 1 that I'd read Southworth's book on waveguides. So last summer I was reading a paper by Zavodsky. Sorry, I'm going to butcher his name here. He was a Soviet physicist, and he was actually one of the pioneers of EPR. I'd seen where one of the universities had set up a museum that shows all of his original equipment to run these experiments. You know, those experiments were conducted in the 30s and then again on into the 40s. So I was looking at what he was able to do with the equipment that he had available, and I thought surely we could reproduce some of these experiments today at a low enough cost that a hobbyist could pull it off. So he's really the guy that got me kick-started as far as doing this video. I'd like to define some of the terms that we're going to be using. The first one is mass. This is a measurement of the body's inertia, or the resistance to acceleration for a given force. An atom is made up of subatomic particles. It's the building block of all matter. A molecule is made up of 2 or more atoms that are chemically bound to one another. An element is made up of only one type of atom, and it can't be broken down any further. An example would be to look at the periodic table of elements. Gold, for example, that would be an element. Atoms, we said, were made of subatomic particles. A particle is things like protons, neutrons, and electrons. Of course, there's many others as well, but for the purpose of this video, this is adequate. So here I have a crude drawing of what an atom looks like. In the center of the atom, we have what's called the nucleus, and the nucleus is made up of protons and neutrons. In the case of a hydrogen atom, for example, the nucleus is made up of a single proton and then a single electron. So this electron is unpaired. So as we look at the atom, we see these different shells. So here's the inner shell, and this can contain up to 2 electrons. Once it gets full, we go to the next shell, and this second shell can have up to 8 electrons. The weight of an electron is 9.1 times 10 to the minus 31 kilograms. On the other hand, a proton is a lot heavier. It weighs 1.67 times 10 to the minus 27 kilograms. You may have heard the term NMR. It's another type of spectrometer. NMRs will work with protons. The type of spectrometer that I'm demonstrating works with electrons. The EPR system works at much higher frequencies than an NMR system. I think the fastest system that's out there today was made by Bruker, and that system runs at 1.2 gigahertz. We'll be conducting these experiments today at about 9 gigahertz. Artistic depictions of the atom have deceived us all. Do electrons orbit around the nucleus of an atom the same way planets orbit around the star? If you think about the way we depict atoms in art, we actually have the nucleus in the center, and that the nucleus, of course, is where you find the protons and neutrons, and then we have electrons in these circular rings around the nucleus. And sometimes in physics, they'll have the rings as sort of nested circles. There are smaller circles, and then there are bigger circles. And we talk about the electrons jumping between those different orbits. Calling what an electron is and where it is around the atom in an orbit is actually very misleading. In truth, electrons don't move around the nucleus the same way that the planets move around a star at all. Elementary particles are not tiny, tiny little balls that are actually moving through space. They're more properly described as waves. And an electron does not exist in only one location around an atom. It actually exists as a wave. A single electron can actually be an entire sphere around the nucleus of an atom. I caution you, nothing's actually moving around like a planet around a star. Some of these orbitals are shaped like dumbbells, and a single electron actually fills out the volume that looks like a dumbbell. It's not that a single electron is moving around inside the shell, it's in the whole shell all at once. There really isn't any circular motion around an atom. It's true that the electrons have an angular momentum, They have something that we can actually measure as a spin, but they're not actually spinning. They're not actually moving around. So despite our depictions of atoms with the nucleus in the middle and the electrons going around the outside, reality is nothing like that. While it is common for electrons to be displayed as concentric rings around the nucleus, they are actually arrayed in three-dimensional series of orbitals that are either types S, P, D, or F. S, P, D, and F. Each and every electron that is found in any orbital has a unique quantum number like the electron's home address. It lists the layer of the orbital group, how many orbital groups from the nucleus it is, the type of orbital the electron is found in, the location within the orbital that the electron can share with another electron, and finally, it lists the spin of the electron, which denotes it from the electron it is paired with. They have the principal quantum number, angular quantum number, magnetic quantum number, and electron spin. It's very important to understand that the electron spin quantum number, ms, is independent of the other three quantum numbers. So in the case of our hydrogen atom, we have a single proton and a single electron. The electron can move from the inner shell to the next shell up where it absorbs energy, or can shift down a shell where it releases energy. I want to be very clear that when we talk about an electron changing shells, that's not the same thing as spin. This is a EPR spectrometer. This type of spectrometer goes by different names. This is a paper published by Gary Buettner from the University of Iowa. So in here he talks about the name electron spin resonance, or ESR, developed from the field of free radicals. The name electron paramagnetic resonance was preferred by researchers studying transition metals. And of course we have the electron magnetic resonance, EMR, which has been offered as an inclusive alternative. However, the name paramagnetic resonance is appropriate from a physics point of view for radicals, transition metals, and solid-state studies. Thus, the International EPR Society recommends the use of EPR. So what is EPR? EPR is a spectroscopy that looks at the environment of unpaired electrons. Electrons have a spin, they produce magnetic field, and thus will behave like little magnets with quantum mechanical characteristics. When placed in a magnetic field, these quantum properties dictate that there are only two possible orientations. Either they're in a low energy or a high energy state. This is a block diagram showing the spectrometer that we're going to be using today. It consists of some type of a microwave source. In our case, that's going to be a VNA. The signal feeds through an isolator and then an attenuator in this block diagram. We have this device here which has 4 ports. This is called a magic T. Up here I have a load. Out here we have our detector and an amplifier and a recorder. Now in our case this is going to go to port 2 of the VNA. This leg here goes down to a resonant cavity and the sample is inserted into the center of the cavity. And then on the outside here I have 2 very large DC magnets. We're going to talk a little bit about spin, and the first thing I'd like to say about spin is spin doesn't mean spin. So an EPR spectrometer uses electromagnets to provide a variable magnetic field over the sample. So in the center here we have our electron, and then on the outside we have our variable magnetic field. So you can see we have the north lining up with the south, north and south, and this is again the low energy state. And then when we go to the high energy state, you can see the north going to the north and the south to the south. So this has actually flipped its orientation or changed its state. And here we're showing an atom. It's got 2 electrons. When we talk about an unpaired electron, we're talking about an atom that has an odd number of electrons. If we look at the periodic table of elements, in the upper right corner, this is the atomic number. This tells us if there's an odd or an even number of electrons. So if we look over here for copper, for example, you can see it has 29 electrons. Or gold down here is 79 electrons. So both of these would have an unpaired electron. Now this particular spectrometer is not good for looking at molecules that use a single atom. So if you go to the periodic table again and you look at like tantalum, gold, magnesium, you can see that all those have an odd number of electrons, but because they consist of a single atom, it makes it very difficult to analyze them. So I'm going to attempt to show you why. So in this demonstration, I want you to view these 2 compasses is two separate atoms, but they're the exact same type. The needle on the compasses, you can think of those as the electron. And as we move these compasses apart, you can see this compass starts pointing to the north direction. Same with this compass here. But as I bring them closer together, you can see now these two unpaired electrons interact with one another. Once these two form this common bond, as I rotate them, they always stay locked together. So let's take our two gold atoms and we're going to put them in our spectrometer. So I've got this bar magnet here. This is going to represent our outside magnetic field. So I'm going to start to bring this bar magnet close to our two atoms, increasing the field. And you can see it's having no effect on our electron spin. It's starting to have some effect. Right there, now you can start to see a little bit of deflection. And if we're looking at other molecules that have multiple atom types, and then one of those atoms has an unpaired electron, then these spread apart. They're not all tightly bundled together like what we would have with gold. And again, as these move apart, that magnetic coupling between the electrons is reduced, and now we can overcome that weak bond with our external magnetic field. So I don't know if that makes sense to you or not. Hopefully it does. Again, not being a quantum physicist, I can't tell you if this analogy is correct or not, but I think it's a good visual representation of what's going on. Typically a spectrometer like this would take up an entire room, and the magnets that they would use would weigh in at about 700-800 pounds, and they're water cooled. For our experiment, we're going to be using much smaller magnets. So this is showing a spectrometer that was produced by Lambda Scientific. This is a model LEAI-15. So off to the right, these are a pair of electromagnets. Down in here is going to be a resonant cavity. So you see off to the left, here we have our source. They have a variable attenuator, goes into the magic T, and you can see part of that signal is going to go down here to the right to our sample cavity. And right here are our two magnets. Part of it goes up into a tuner stub into the terminal load, and then the other leg of the T goes to an isolator into the detector. This isolator here is basically nothing more than a diode, I guess is how you could look at this. So this allows the RF energy to pass only one direction. You may remember in that first video I had taken some ferrous material and I placed that into a waveguide, and then I took a magnet and I stuck it to the outside of the waveguide, and I was actually changing how much that material absorbed. That's basically what's going on with this isolator. So what we're trying to analyze, or our sample, will fit inside of this sample cavity. You'll notice that they show kind of a piston here. That's so we can change the resonant frequency of the cavity. We'll be doing something very similar to this, except we'll be using the Light VNA 64 for the source as well as the detector. You can see this particular one has been modified to include this additional SMA. What I've done with this one is I've removed the 24 megahertz oscillator and I've replaced that with this SMA jack. So what I'll be doing is driving this with an external reference, which will be tied to my GPS receiver. While we're looking at this block diagram, a couple of things that I'd like to mention as well. On a production type spectrometer, they will have some type of a field measurement sensor, like a Hall sensor for example, that will sit outside and monitor what the flux density is through this resonant cavity, and they'll close the loop on that. And again, looking at this paper from Brooker, the magnetic field regulation occurs via a Hall probe placed in the gap of the magnet. The relationship is not linear and the voltage changes with temperature. However, this is easily compensated for by keeping the probe at a constant temperature, slightly above room temperature, for characterizing the nonlinearities so that the microprocessor and the controller can make the appropriate corrections. Another thing that is quite common is they'll have another set of coils that are sandwiched around the outside of this cavity, and they'll modulate these at a low frequency. So typically they'll have a lock-in amplifier as part of their detection scheme. The reason they're doing that is to increase the sensitivity. Now, I'm not going to be doing anything like that with our spectrometer. A couple other things that we should mention about these spectrometers: they're affected by temperature, and as temperature goes down, the sensitivity goes up. Likewise, if the frequency goes up, the sensitivity increases as well. Another benefit of increasing the frequency is the physical size of the sample decreases. Of course, we mentioned the Q, or the quality factor of the resonant chamber. As that increases, of course, the sensitivity increases as well. I've seen typical numbers published for the X-band where they run between 3,000 and 3,500 Gauss. That's certainly not set in stone. Looking at our university test spectrometer, you could see they had an operating frequency of 8.6 to 9.6 gigahertz, and they provided a field strength between 0 and 450 millitesla, or 4,500 Gauss. So 1,000 Gauss higher than what I've seen mentioned in other papers. These components came from a university waveguide training kit. Here we have our coaxial transitions. This device here is called a Hybrid Magic T. The device here to the left, this is our load. To the right, this is a tuner. And then to the far right, this is a resonant cavity. So let's talk a little bit about this Magic T. You can see it's nothing more than a hollow piece of tube. There's nothing inside of it at all. So if we inject RF into this facing port, it'll either go to the right or to the left, but nothing will come out of the top port. Likewise, if I inject RF into this top port, it'll also go to the left or to the right, but it won't come out on this facing port. So if we look at this device here, if we were to inject our signal here, again, the signal is going to go to the left and it's going to go to the right. To the left, it has a terminator, so that's going to absorb all that energy. The signal that goes to the right will go through this tuner into this cavity, and depending how well this is tuned, hopefully very little signal comes back through the tuner back into the Magic T. Once it hits this port here of the tuner, the signal is either going to go up or it's going to come out the facing port, but none of it will continue on through to this port. Now we know that this terminator is not perfect. It's going to have some reflection as well. So some of that signal, again, is going to be reflected back into this port. That signal is either going to go out this direction to our input port, or it's going to go up to this top port. But none of it will go down this direction towards the tuner. This is the page out of the manual. It's talking about the Magic T. This one actually specifically. They call this the H-plane shunt arm. The top we call the E-plane or series arm. And then the left and the right are called the main guides. This T is a combination of both the E and the H-plane T. The input is applied to the H arm and divides equally between both main arms. And these outputs are in phase. No power is found at the E-plane arm. If the input is at the E-plane arm, the output is divided equally at the main arms and the signal is out of phase. No power is found at the H-plane arm. If we apply two signals, one at each main arm, the output at the H-plane arm is the sum of the two signals, but the E-plane arm is the difference between the two signals. So one way to look at this is I have a source. It's going into my bridge. I've got one fixed resistor, which is this terminator on one leg, and the other one I have this resonant cavity, and I'm essentially looking at the voltage across this. So you can think of this as a bridge, and you'll see some papers when they're building these spectrometers actually refer to this as a bridge type. The splitting of spectral lines when an atom is placed in an external magnetic field was looked for by Faraday, predicted on the basis of classical theory of Lorentz, and first observed by Zeeman. In quantum mechanics, a shift in the frequency and wavelength of the spectral line implies a shift in the energy level of one or both of the states involved in the transition. So if we look at our VNA, we have two ports. There's a port 1 and a port 2. Port 1, we can measure the incident as well as the reflected signal. So it's not just the magnitude, we can look at the phase relationship between the two signals. It's a vector number, hence vector network analyzer. So essentially with port 1 we can look at S11. With port 2 we can look at the transmission of the signal from port 1, and that's S21. So this again is a two-port single path VNA. If I apply a short from port 1 to port 2, the output signal of this is going to be 0 dB. Again, that's a relative number. Of course, this is going to go up and down if we look at the absolute value, because the output signal of this is certainly not flat, but relative wise it's going to be 0 dB. We're looking at our spectrometer. Again, these are two ports that are going to the VNA, and let's just call this our port 1 here. Again, we said the signal goes in here, propagates to the left and to the right, goes into our resonant cavity, and this absorbs all the signal, and our load here on the left also absorbs all the signal. So assuming that this is in resonance, the output signal on port 2 here is going to be a very low value. Now as the cavity is tuned out of resonance, all that signal reflects back. Again, that signal would go up, and it would also go back towards the input port. Now again, we're sweeping from a low frequency to a high frequency. We're looking at port 2. When that cavity goes into resonance, it's absorbing all the energy, and we see no signal difference between the two. Once it falls out of resonance, again we get a high signal because all that signal is being reflected back from the cavity. If we had a cavity that kind of looked like this, for example, this is going to be a very sharp Q, versus this, the Q isn't as good. So the wider it gets, the worse the Q is. So we're trying to tune this cavity to give us a very sharp and deep notch here. So again, getting back to the Zeeman effect here and what they said, that a shift in the frequency and wavelength of the spectral line implies a shift in the energy level of one or both of the states involved in the transition. What's going to happen with this, if we put in something inside of this resonant cavity here and it goes through a state change, we're going to see this thing shift. I can sort of understand what's going on at the atomic level, but not really. It's quite a bizarre thing. I was hoping that by conducting some of these experiments I'd gain a better understanding of what was going on, but I can tell you that's not really been the case. So I would like to give a shout out to a friend of mine that I met on the internet. Basically, he specializes in EPR, and he's been a big help. I won't mention his name here. I just want to let him know that, hey, I appreciate all the help that you've given me. So are materials with unpaired electrons magnetic? Most materials with one or more unpaired electrons are at least slightly magnetic. Materials with small attraction to a magnet are called paramagnetic materials, and those with a strong attraction are called ferromagnetic materials. Aluminum, platinum, magnesium are some of the paramagnetic materials. Iron, cobalt, nickel are examples of ferromagnetic materials. So EPR is a magnetic resonance of an unpaired electron. Species that can be studied with EPR are free radicals. Free radicals would be like vitamin C, for example. Transition metals with odd number of electrons or high spin. Excited states with S not equal to 0, or triplet states. Molecules with all electrons paired have no electron magnetic momentum, hence no EPR spectrum. So it has to work with molecules that have an unpaired electron. Compared to NMR spectroscopy, the resonant frequency for a free electron is about 600 times larger for a proton than for a proton in the same magnetic field. In atoms and molecules, the electrons have both orbital and spin angular momentum. Each of these generates a magnetic dipole moment. Most experiments, the absorption is measured as a function of frequency. In EPR experiment, the absorption is very weak, and this method is only feasible at very high magnetic fields. To overcome the problem of weak signals, a resonator is used. The sample is placed in a resonant cavity such that it sits in the magnetic component of the resonant microwave field. So here we have a cross-sectional view of the waveguide. You'd be looking down the waveguide tube here. Here we have our electric lines of force, and here are our magnetic lines of force. Our sample is sitting right in the middle of this cavity. Wave propagation, of course, is this direction, and we're talking about the TE mode. Microwaves are usually brought to the resonator using waveguides. An iris is placed at the entrance of the resonator to couple it. This is just some of the examples for iris geometry and what their counterparts look like. So again, we said if it's a circle, it behaves like an inductor. Here we have an inductor in series with a capacitor. Here we have an inductor in parallel with a capacitor. These are capacitors. Again, this would be the open area. And here we have inductors as well. And again, this is looking at a cross section of the waveguide. So you're looking down the length this way. So here's the microwaves coming in. We reach this iris right here. And we have this set screw in front of the iris. And this is closed off. And this is forming our resonant cavity. And again, our sample will be placed in the center of this. By adjusting the shape of the iris, the source is critically coupled to the cavity and no power is reflected. Of course, if it's resonating, that's the whole idea, right? Nothing's getting reflected back. When they talk about critically coupled, we're talking about something in the 70 dB, maybe even more. So again, if this coupling is poor, let's look at the worst extreme. Basically, nothing is being absorbed. We're not going to be able to detect our signal on top of this. So typically with this type of spectrometer, we're trying to get a very good resonant point or very good Q of our resonant cavity or quality factor. This basically explains what's going on. When an EPR transition occurs in the sample, the resonance is disturbed and the power is reflected. So again, looking at our little model of a spectrometer and thinking about our outside magnetic field placed around our resonant cavity here, there's two ways that we can run this type of spectrometer. We can either hold the frequency that we're operating at constant, and then we can vary the flux density through our cavity, or we can hold it at a constant flux density and then vary the RF frequency. Now all the EPR spectrometers that are produced, they all work the same way where they hold the frequency constant and then they vary the flux density. Now this paper that I found tries to give a little insight as to why that is. A radiation source for radar waves produces only a very limited spectral region. In EPR, such a source is called a klystron. A so-called X-band klystron has a spectral bandwidth of about 8.8 to 9.6 gigahertz. This makes it impossible to continuously vary the wavelength similarly to optical spectroscopy. It is therefore necessary to vary the magnetic field until the quantum of the radar waves fits between the field-induced energy levels. You'll notice I got a little frowny face on here. I don't believe that this statement is true. Maybe at one time the author felt it was true, but being a double E, I can tell you that we don't use klystron tubes anymore. Working over a wide range of frequencies is not an issue with modern test equipment, but these types of spectrometers continue to use fixed frequency. Of course, that's not because of the history of starting out with a fixed frequency system. Let's think about it. Again, we said we're working with a very sharp Q. So in this case, we have a tuner on the front end, or our iris, and then we have this one setting the size of the resonant cavity. So we've got these two adjustments that are moving simultaneously while we're changing the frequency. You could imagine to make that work would just be a mechanical nightmare. I'm not saying that's not possible, but I am saying that I don't agree with this paper. The real reasons for making the spectrometers work with a fixed frequency has nothing to do with this klystron tube. It's all about the mechanics of the waveguides. So when we're looking at different molecules, they all have a unique G factor. The G factor is a dimensionless constant for any given species. For free electrons, G is equal to approximately 2.002. Beta is the Bohr magneton, and H is Planck's constant. c is of course the speed of light. So here we're talking about the energy of the microwave radiation is connected to the resonance by this equation. So delta E equals HV, which equals GBH. So G again is this dimensionless quantity that we talked about. B is beta, or the Bohr magneton, and H is Planck's constant. So we can see that H and B are physical constants, and G is a constant for any given species. Thus the only variables of the equation are V and H. So basically we can change the flux density and we can change the frequency, but everything else is constant. Here they make a comment, it is not possible to vary the wavelength or the frequency of the instrument for an experiment. Thus the frequency of each experiment is fixed and the magnetic field is varied. The sample is placed between two poles of the electromagnet of the spectrometer and the magnetic field is swept. This is how all spectrometers work. So again, this G factor is a constant for any given species, but can vary considerably from species to species. G depends both on the spin of the electron as well as the orbital angular momentum of the electron. G will have information about the electronic structure as well as the symmetry of the system. And then this is the calculation to determine at what point we see these spin transitions occur at. This is a paper called EPR Primer that I found on the internet. The two spin states have the same energy in the absence of a magnetic field. Without a magnetic field, there is no difference to measure. The measured energy difference depends linearly on the magnetic field. A peak in the absorption will occur when the magnetic field tunes the two spin states so that their energy differences matches the energy of the radiation. Here they're showing a table of various frequencies that could be used for EPR spectrometers. So the one that we're interested here is the X-band, and they're operating at a frequency of roughly 9.75 gigahertz. And then this is the magnetic flux density in Gauss. So that's typically running about 3480 Gauss, or 348 millitesla. Here they're showing a commercial spectrometer by Brooker. Here we can see the large electromagnets. Down here is our resonant cavity, which holds our sample. Off to the left here he's got his magnet power supply and his Linux workstation. And here he's kind of showing a schematic of it. In this case they're using a circulator. In our case we'll be using again the Magic T. Most EPR spectrometers are reflection spectrometers. They measure the changes due to spectroscopic transitions in the amount of radiation reflected back from the microwave cavity containing the sample. We therefore want our detector to see only the microwave radiation coming back from the cavity. Again, we use microwave cavities to amplify weak signals from the sample. A microwave cavity is simply a metal box with a rectangular or a cylindrical shape which resonates with microwaves much as an organ pipe resonates with sound waves. Resonance means that the cavity stores the microwave energy. Therefore, at the resonant frequency of the cavity, no microwaves will be reflected back, but will remain inside of the cavity. Of course, the cavities are characterized by their Q, or quality factor. As Q increases, the sensitivity of the spectrometer increases. Energy can be lost to the sidewalls of the cavity because the microwaves generate electrical currents in the sidewalls of the cavity, which in turn generates heat. A consequence of resonance is that there will be a standing wave inside of the cavity. Standing electromagnetic waves have their electric and magnetic field components exactly out of phase. We can use the spatial separation of the electric and magnetic fields in a cavity to great advantage. Most samples have a non-resonant absorption of the microwaves via the electric field. This is how a microwave oven works. And the Q will degrade by an increase in the dissipated energy. It is the microwave magnetic field that drives the absorption in EPR. Again, we couple the microwaves into the cavity via a hole called an iris. The size of the iris controls the amount of microwaves which will be reflected back from the cavity and how much will enter the cavity. The iris accomplishes this by carefully matching or transforming the impedances, or the resistance to the waves, of the cavity and the waveguide. So again, we're just trying to match that waveguide to the cavity. And again, this is what I was talking about. There's an iris screw in front of the iris which allows us to adjust the matching. This adjustment can be visualized by noting that as the screw moves up and down, it effectively changes the size of the iris. So again, looking at our mock-up spectrometer, again we have this cylindrical cavity. Now if I were to take this apart, you would see a plunger in here that can slide up and down as we adjust this micrometer in and out. Again, we're changing the volume of this cavity. And then if we look down inside of the cavity, we would find a small slit at the base of this that protrudes through to the inside of the waveguide. That's how we couple the RF up into the cavity. Now, if we wanted to actually analyze a sample, somehow we got to get that inside of this cavity. And you can see this isn't really set up for that. The other problem with this is you can see we just have this end capped off. So any of the signal that doesn't get absorbed up inside of the cavity is going to hit this plate. Of course, it's going to bounce back. So this is not an ideal arrangement. Really what we want is a rectangular cavity. So what I had done early on is I purchased this. This is an old adjustable short that was produced by HP as a Model X for the X-Band 920A, Hewlett-Packard Company. You can see it's got this little crank knob, and what that does is it moves this little piston in and out of the waveguide. You can see it's coming out, and here it's going down inside. Ideally, this is what we want for our cavity. Now, I had mentioned we have to have our little slit, or again, we call that an iris. So here we have an iris. Again, the shape of this iris defines what the equivalent circuit is. This would mount to the front of the cavity like so. And then we would have an adjustment screw that would fit right in front of this that could be moved up and down. Again, essentially changing the area of the hole or adjusting the tuning. So we use the crank here to set the resonant frequency, and then we use the set screw to perform the match. Now there's still a problem where we would have to introduce the sample inside of this cavity, and the way that we would do that is we would drill a hole into the waveguide, and then we can just insert our sample down into the center of this. So we'd have some small test tubes like this one here, for example, that would just fit down inside of this like so. Now these test tubes have to be made out of quartz. As a matter of fact, there's companies that make test tubes specifically for this type of spectrometer. The whole key with using quartz is it's a lot more pure than what glass would be, for example. Again, keeping in mind that that's going to sit inside of this resonant cavity. So when we run the spectrometer, this is going to interfere with that measurement. The more that we can make this transparent to the measurement, the better. Again, this is the light VNA that we'll be using to conduct these experiments. You can see that this is hardware revision 64.0.3. This is the original light VNA 64 hardware. Again, it has been modified to include this external reference port. I also have this one, and this is the latest hardware. You can see on the back, this one is 64.0.31. Now this VNA actually has a little bit better performance than the older one, so you may wonder, why aren't we using the new hardware? Well, it turns out there's a problem with this. The whole reason, again, that we've added this external reference is I'm looking for a very stable output frequency. So when I started testing this particular VNA, and I'm looking for changes of 1 hertz out of 500 megahertz in this case, what I noticed is this particular hardware will dip about 50 hertz or so. It's just random. So you'll see the frequency running along at 500 megahertz, and then it just drops by 50 hertz, and then it recovers. And sometimes later it drops and it recovers. I don't know what the cause of that is. I tried every version of firmware that I had. It did it since day one. I just never noticed it. Normally under normal operation, it's not anything I'd even be concerned with. But in this case, that could be critical. This hardware, with the exact same version of firmware of this, doesn't exhibit that problem. Now I have a second original Light VNA 64 that's identical to this. It just hasn't been modified. I tried running the tests on that hardware as well. It also doesn't exhibit that problem. So something's going on with the new hardware. I don't know what the problem is. I've posted some information about that up on the internet. Maybe the developers will correct that in the future. But for our testing, we'll be using the old hardware. Now you may remember that the Light VNA has a frequency range of 50 kilohertz to 6.3 gigahertz. Now DiscLord had released firmware that allows us to use harmonics with this VNA, but the whole problem with doing that is the dynamic range really suffers. So if we look at S21 at 9 gigahertz, I believe it's like maybe minus 10 dB or so. So the performance isn't near good enough to use harmonics. So the way we're going to work around that again is we're going to use our frequency extender. So you may remember in the first sets of videos I had shown this. Of course, it's been rebuilt slightly. It's now inside of this box. This is closed off on all the sides. Now this is basically the same circuitry that I showed in the very first video. You may recall that the original frequency extender, I used a directional coupler that I think was rated for like maybe 8.3 gigahertz or something. The other problem with that coupler is the directivity was pretty poor. So this coupler is also made by Narda, but it's rated for a much higher operating frequency, and it also has a much higher directivity. So using this coupler, we've greatly improved what we can measure using this frequency extender. The other thing that I've changed with this extender is I've added an internal RF relay, and that allows us to measure either S11 or S21. This is the external 10 megahertz reference for the phase lock loop. This is our power input connector. These two connectors go off to the Light VNA, and you'll see at the base here it's marked 40 megahertz to 4 gigahertz. That gives us an operating frequency range of 8 gigahertz to roughly 12.5 gigahertz. Again, internally this has a DRO, and the reference frequency for that is 7.86 gigahertz. So this is looking at the actual spectrometer that we'll be using to run these experiments today. Off to our left, this is the resonant cavity. This piece here is our iris. Here's our magic T. Back behind, this is our load. This is our isolator. And then we have our two transitions that'll be connecting up to the VNA. Again, the signal is injected on this port. The RF travels down through the isolator. Again, this isolator only allows the RF to travel in one direction. Anything that reflects back through to the isolator from this direction will be absorbed in heat, just like our load in the back. Again, as the signal propagates down towards the magic T, it's either going to go to the right towards the load, or it's going to go to the left to the resonant cavity. But no signal is going to come up to the output port here. Again, this is a very good load. You can see it has a VSWR of 1.015. So the return loss off of this is going to be very low, but the signal that does return is either going to go up to this port, or it's going to go back towards the isolator, where again it'll be burned off in heat. As the signal moves to the left, again it goes through our little slit or our iris and then into the resonant cavity. Off to our left, you can see I have a micrometer. This is moving a piston back and forth inside of the cavity, again changing the volume of the cavity or its resonant point. Up here we have another adjustment screw. This set screw sits in front of the iris and again changes the area of the iris or matches the waveguide to the cavity. This piece here, this is a pole piece. Here we have this horseshoe magnet. We have a north and a south pole, so this is an open circuit. So just like an electrical circuit, adding this bar across the two poles closes the circuit. This is the same thing that this pole piece is for. So the path actually goes this way and then up and around the loop this way, back through. And it also goes this way through the bottom and then back through. What we're trying to do again is get some very straight flux lines through the center of our resonant cavity here. So the stack here to the right, this is basically what that's made up of. So there's a permanent magnet, just like this one here. And then there's a series of brass and iron shims that are stacked up. So as I pick different combinations of brass and iron, I'm essentially changing the air gap in that circuit. And what I'm doing there is I'm controlling the static flux density going through that waveguide. One of the things I should mention is that while I'm using these fixed magnets in combination with this electromagnet, spectrometers like this type will normally use electromagnets only. That allows them to operate over a much wider range. Of course, the magnets for those systems are much larger than this, and it also requires a lot more current to drive it. For these experiments, we don't need that kind of range, so I've opted to use this scheme. I'd like to give a shout out to my buddy Scott, who made this pole piece for me. I believe that they laser cut this and then bent this in a press, and then this was welded together and finally powder coated. It's a very nice piece of workmanship. So the right side again is our permanent magnet. The left side is a solenoid. We've set this magnet and air gap up on the right to give us about 3,000 Gauss. And then this magnet on the left, we can use that to increase the amount of flux density through the tube, or we can actually decrease it by changing the polarity. Now as we're driving this coil, of course it's going to heat up, and that means its resistance is going to increase. And because we're looking for a constant flux density, we're going to drive this with a constant current source. So this is converting a voltage from a DAC to a current that's driving the coil. Again, we have our test tube, which would normally have a sample, and we slide that down inside this hole here, and that introduces the sample into the center of the waveguide. Now when we hook up the light VNA and we use that external clock reference, the output frequency off of that light VNA is very predictable. So we don't have a problem with that, but again, we're driving this coil with this constant current load, and we really need to know what the flux density is through this. So somehow we got to get from voltage to flux density. So the way I measured that is I purchased this cheap Gauss meter. This is a Tunkia, I guess. It's a model TD8620. You can see it has two different ranges, 200 millitesla and 2000 millitesla. We'll be conducting our experiments between 300 and 350 millitesla. You can see the accuracy for the Dash 5 is plus minus 2% between 0 and 1000 millitesla. This particular Gauss meter was supplied with a transverse probe. If you look at the probe this way, magnetic fields can go this direction versus this way. This is looking at the probe. It's got a protective cap. You should always leave this in place. Here's the Hall sensor. We take this sensor and we slide this down inside of the sample hole, and we line that up to get our maximum flux density. Once I have that, I lock the probe in place, and then I go ahead and sweep the coil, and I measured, in my case, 6 different data points. I use that to create some coefficients for a 5th order polynomial fit. This is the actual Gauss meter here. You can see it reads in Tesla, or it can read in Gauss. These meters are available on eBay as well as Amazon. This did not cost a lot of money. I'm sure it's not very accurate, but for these experiments, this will be fine. Here I have our probe placed into the center of the cavity, and then I've adjusted this for a peak reading. You can see our static field is reading about 312.4. What I'm going to do is adjust our DAC to the maximum setting, and you can see we read roughly 349.2. So with our current shim adjustment, this is our range of operation. So this is the entire mass spec all assembled. In the center we can see the light VNA 64. Beneath that is the frequency extender. This cable runs off to our 10 megahertz reference. This cable for our 24 megahertz reference is going to go to our signal generator. That signal generator is also referenced to the GPS receiver. Again, the extender attaches to our 2 couplers. Again, here's where we inject our sample. Back here I have a cooling fan. Again, that's to blow air across this coil. We just want to keep the temperature of this as stable as possible. Down here is the current controller. This connects to our DAS, which is tied to Ethernet back to the control PC. And you have the USB cable that's also going to that control PC. Here I have some different test chemicals that I've prepared. Let me just give a shout out to my buddy Flipper, who purchased these light VNAs for me, as well as the original Nano VNA. That was in an effort for me to teach him how to use a VNA. That's kind of where all this stems from. He made a comment that it's kind of comical. Here you have a $120 VNA, but the cost of everything that it connects to run this experiment far exceeds what the price of this is. So let me go ahead and I'll show you what the software for all this looks like. So to run the spectrometer, I've gone ahead and modified my solver software for the light VNA. And again, this software is available for free if you want to try and use it. If we go to the Advanced tab, there is now an EPR tab. So down here in the lower left are some of the basic equations. These first two columns on the left are for EPR. The two on the right are for NMR. So here we have an electron charge in electron mass. And we can use these to calculate the Bohr magneton. And from there we can calculate H over beta. This is this 0.714484. Notice that there is a slight discrepancy between the two numbers. I believe that this number here is more accurate, but in the big scheme of things, it really doesn't matter. Down here we define Planck's constant. Of course, we're working with an NMR system. We have the proton charge and mass. And in place of the Bohr magneton, we have the nuclear magneton. Other than that, the equations for the two spectrometers are basically identical. So you can see the H over beta for the NMR is quite a bit higher. This is the ratio between the two types of spectrometers. Down here we have the proportionality factor. This is the value of G for a specific chemical. So for DPPH, which is one of the chemicals we'll be using, if we're looking at G for an electron, it's 2.0036. If we're looking at G for a proton, it's 5.5850. So that's the number here for an electron G, and here for the proton G. So from this we can calculate the value of Gauss where the spin takes place at. So for the EPR system, it happens at 3225.6 Gauss. If we were trying to run an NMR system at 9 gigahertz, it'd require 2,124,744 Gauss. That's a very big magnet. That's really what's limiting the frequency that we can operate an NMR system at. So if we were to take this number down to something more reasonable, say down to 20 megahertz, it requires 4,700 Gauss. Pretty much in the same range that we're running our small EPR spectrometer at. I've included this calculator in my software to give me an easy way to calculate where this transition should occur at. Remember, we took our flux density probe and we placed that inside of the waveguide, and then I said that we swept the voltage, and then we measured the flux density. So these are the 6 data points that I captured from 0 volts to 5 volts. So at 0 volts, the permanent magnet is producing 3129 Gauss. Now as we increase the voltage, of course we're increasing the current through the coil, and then the magnetic field of that is adding to what our permanent magnet is producing. So we can see the flux density is increasing all the way up to about 3500 Gauss. And of course, if we plot that curve, we can see it's not linear once we get above about 3400 Gauss. So I'll run this through a polynomial fit to try to correct for the nonlinearity. Off to the right, this controls our sweep. So we have a start voltage, a stop voltage, and then the resolution, or how much I want to step the voltage by. And then the DAC value is the actual output voltage to the DAC. Up here I have a selection for baseline correction. I'll explain that in a little bit. So currently you can see our solver software is set to sweep between 8.5 and 9.5 gigahertz. And you can see we're looking at S21, or the transmission between the two ports. You can see the dip near 9.4 gigahertz. That is the resonant frequency of the cavity. You can see as I adjust the micrometer outward, the resonant frequency decreases. Of course, we're increasing the size of the cavity. Likewise, if I adjust it inwards, we're increasing the resonant frequency. We'll adjust our micrometer so we're up around 9.4 gigahertz again. Now what I'm going to do is take this empty test tube, again this is made of quartz, and I'm going to start to insert this into our resonant cavity. And watch what happens with our resonant frequency. See how it's decreasing? And again, as I start to remove it, see how the frequency increases. It'd be very nice if this test tube had no effect on the resonant frequency. The only thing I should mention is you'll notice that the VNA has not been calibrated. Again, these measurements that we're going to be taking with this spectrometer, it's always a relative measurement, so there really isn't a need to actually calibrate the VNA. Again, we have various test samples here that we can now insert into our spectrometer and try to analyze them. So we're going to start with DPPH. These little rubber O-rings basically act as a stop. So when I insert this into the resonant cavity, we always have it at basically the same location. What I'm going to do next is change the frequency range of our light VNA. You can see the center frequency is now about 9 gigahertz with a span of about 200 megahertz. Now what I'm going to do is adjust this micrometer to center up our resonant point. So somewhere in this region. Now what we'll do is readjust our span to zoom into this a little further. You can see I've saved this as a reference point. Now we're going to adjust the iris and see if we can improve the Q. And you can see how it's starting to dip as we improve our port match. You can see at resonance we're measuring roughly minus 58 dB. I'm going to turn off our max hold and I'm going to center the waveform. Alright, next we're going to go to our advanced menu and we'll select our EPR menu. So we're going to sweep between 0 and 3 volts on the DAC with a 20 millivolt resolution. Let's go ahead and we'll just run a sweep. We'll save this to the default record file. Let's go to main and let me just save the max hold here. You get an idea of what S21 looks like while this is sweeping that magnetic field. In the top you can see it's displaying the DAC voltage. You can see it's currently 0.7 volts or 3180 Gauss or so. And look at what's happening. See, we're at about 3225 Gauss or so. And now we're back to 0. What we can do is have this scan a little bit faster, so I'm going to set the number of data points to 200. Let's go ahead and we'll change this to a span of 2 megahertz. And again, we'll enable our max hold. And we'll just leave it at 20 millivolts resolution right now. And let's go ahead and hit sweep. We'll just save it to the same record file. So again, we're at roughly 3145 Gauss. Right here you can see how it's starting to change at about 32.2. And we're back to 0. Let's have a look at what that data looks like. So we'll go post-processing. We'll do add waveform and we load up the record that we just created. So this is what it looks like. You can see we have this nice dip at the resonant frequency. We'll change this over to actually look at S21 mag and we'll select narrow band. So this is our center frequency of 9.0475 gigahertz, and again we have our span set to 2 megahertz or plus or minus 1 megahertz, and we have this distinct line right here. See that? Let's change our time axis here to flux density. And you can see it roughly 3220 Gauss. We have this switch point. Again, we're running at 9.047 gigahertz. If we go back to our calculator, and we're running at 9.047, and we are running DPPH, so DPPH has a proportionality factor of 2.0036. So that means our switch point should be at 3226 Gauss. Again, looking at our data, you can see we're spot on with that. So one of the problems with this system is that the longer that we run it, the coil starts to heat up as we push more current through it, and we get a temperature shift. So one way we can combat that, if we go back to EPR, you can see it has this baseline correction. So what this will do is this will take a baseline measurement with the current set to 0, and then it'll set it to the target current, and then it'll subtract off that baseline. So as the coil begins to heat up and we see this temperature shift, we're always going to be subtracting off that error. So let me just show you some of the data I've collected with this spectrometer. We'll select Add Waveform and EPR Experiment. So this is the very first time I ran the spectrometer, looking at the DPPH. Again, we're running at a frequency of 9.044 gigahertz here. And we can clearly see the switch point. Here I was doing a back-to-back test where I'm using this baseline correction. This is the very first sequence I ran, and you can see we get a real clear image now of where that switch point happens. Again, this is running at 9.0048 gigahertz, so it's changed the flux density slightly. Let's compare that with the last one I ran. So again, these are all back to back, and you can see they're very similar. Right here's the switch point. The other thing you'll notice is the dip changes a little bit as the resonant frequency changes. But what we're really interested in is where that state change occurs at. Looked at other chemicals, so this is calcium oxide, for example, and you'll notice that there are 2 lines. There's actually 6 lines with this type of chemical. Unfortunately, with this spectrometer, I'm not able to adjust the range of the magnetic field enough to actually see all 6 of those. The distance between these 2 peaks is supposed to be about 80 or 85 Gauss or so. One thing I had forgotten to mention, when we were looking at the calcium oxide, and then I said it had 6 different transitions, calcium oxide apparently contains trace amounts of manganese. And it's the manganese that actually has the unpaired electron. Well, I think that's going to be it for this video. Hopefully you found it interesting. To me, it was fascinating that we could put something together on a hobbyist home budget using a $120 VNA that we could actually use to measure quantum state changes in an atom. It's just mind-boggling. Well, that's going to be all for now. Hopefully you enjoyed the video, and hopefully we'll see you in the next video. Later.